In a special function, till now we have discussed Legendre's polynomial in detail. You have seen the all aspects of Legendre polynomials, like recurrence formula regarding the Legendre polynomial, Rodriguez formula, the orthogonality property of Legendre polynomials. Today, in fact, we are now going to discuss another important special function related to this Legendre polynomial, and that is actually called associated Legendre polynomial. In fact, like Legendre polynomial, this associated Legendre polynomials also find their applications in solving the problems of physical interest, or you can say in solving the problems of physics. This polynomial has a vast application. So first of all, we will see what is this associated Legendre polynomial, and then we will see some of its important properties. So to define this associated Legendre polynomial, first of all we have to see a particular differential equation which is known as associated Legendre equation. You can see I have defined this associated Legendre equation in this way. In fact, this is defined as 1 minus x squared d2f by dx square minus 2x df by dx plus lambda minus m square over 1 minus x square f equal to 0. Here f is actually a function of x. So this equation, which I have mentioned in this equation A, is known as associated Legendre equation. In fact, in this equation, this term lambda is equal to n into n plus 1. And this n is what? Actually, this n is, you can see, a positive integer. Remember, n will be never a negative integer. It is always a positive integer, and this n can assume only positive integral values. And this m, what is this m? Actually, m is also an integer, but this m may be positive, it may be negative, or even it may be 0. Actually, the equation A, which is known as associated Legendre equation, in fact, solutions of this equation, which are actually finite everywhere in the range, you can see here, minus 1 less or equal to x, and this is less or equal to 1, after satisfying certain normalization condition, are actually known as associated Legendre's polynomial. So in brief, you can say the solutions of this equation A is known as associated Legendre's polynomial, and that will be, in fact, that will give actually finite solution of this equation only in this range. See here, x must lie between minus 1 and plus 1. In fact, we will denote this associated Legendre polynomial by a particular symbol. You can see here. This is denoted as Pnm of x. And as you know, the solution of this associated Legendre equation defined in equation A is associated Legendre polynomial, which we have denoted by the symbol Pnm of x. So this f, which is solution of this equation A, is that simply this associated Legendre polynomial. So you can say that f of x is equal to Pnm of x. Now we will consider actually two cases for the sign of m. First of all, I am considering that m is a positive integer. As I have told you that this m may be positive, this may be negative, or it may be even 0. So first of all, I am considering that m is a positive integer. So let us first assume that m is a positive integer. M is a positive integer. In fact, I am considering this first. In fact, when you will consider that m is a positive integer and you write a particular value of this function f of x, so you can say if we write f of x equal to, you can see this f of x is what? This is simply Pnm of x, which we call associated Legendre polynomial. So this, if we write this f of x equal to Pnm of x, and this is equal to 1 minus x square raised to the power m by 2 f of x, capital F of x. See here, this is capital F of x. This is an arbitrary function. So if we define this function f of x, or you can say the associated Legendre polynomial Pnm of x in this way, then what will happen? In fact, you can find the first order derivative of this f of x, or you can say this Pnm of x, and also the second order derivative of this f of x. And after finding df by dx and d2f by dx square, we will simply substitute those two values in this equation A at the place of d2f by dx square and df by dx. In fact, when we will do this algebra, that we will get a particular equation, you can see. So if we find df by dx and d2f by dx square and substitute these in equation A, that is associated Legendre equation, in equation A, then after simplification you will get a particular equation. I am actually writing that particular equation directly. You can do the algebra yourself. So try to do those algebra. First of all, you will differentiate this equation with respect to x, and again we will differentiate that equation with respect to x to get the first order derivative of f and the second order derivative of f. And when once you know the value of df by dx and d2f by dx square, then you have to substitute those two values in equation A. Then we get, I am writing the result directly here. You can do the algebra. You will find after substituting these two values, our result will be 1 minus x square d2 capital F, this capital F, by dx square minus 2 times m plus 1 x df dx. This is capital F, see here, and plus lambda minus m times m plus 1 f, capital F, and that will be equal to 0. Let us say this is equation 1. I have not done the algebra, you can do it yourself. So try this. Find first of all df by dx and then d2f by dx square, simply differentiating this equation B, and after that substitute these two values in equation A. Then after simplification you will get the result which I have defined in this equation 1. Now you know that what is Legendre's equation. You have already studied it, and you know Legendre's polynomial are actually the solution of Legendre equation. So definitely you can write the Legendre equation in terms of Pn of x, that is, instead of y we will write Pn of x. So we know Pn of x are the solutions of Legendre equation. And if these Pn of x are Legendre solution of Legendre equation, then definitely this Pn of x, which is called Legendre polynomials, these will satisfy the Legendre equation. So you can write, so Pn of x satisfy Legendre equation. And so you can write Legendre equation in terms of Pn of x. This will be 1 minus x square d2 Pn of x dx square minus 2x dPn of x dx plus n times n plus 1 Pn of x equal to 0. You can see this is simply a Legendre equation, and as I have considered this product n times n plus 1 equal to lambda, you can see here we have actually assumed that this product is actually equal to lambda. You can see here. So in this Legendre equation you can substitute lambda instead of n times n plus 1. So you can write this is 1 minus x square d2 Pn of x dx square minus 2x dPn of x dx plus lambda Pn of x equal to 0. Say this is equation 2. Now, if you will differentiate this equation to m times, in fact m is a number, and when we will differentiate this equation to m times, and assuming that m is a positive integer, I have considered that case, then after some calculation you will get a particular equation. So I am again not doing all those algebra here. You can do it. Simply differentiate this equation to m times and consider that m is a positive integer, and after that we will get a particular equation which I am writing here directly. So if we will differentiate equation 2 m times, assuming m to be positive, then we get this equation. You can see 1 minus x square d2 dx square dm dx m Pn of x and minus 2 times m plus 1 x d dx dm dxm Pn of x and plus lambda minus m times m plus 1 Pn of x equal to 0, and say this is equation number 3. So we have obtained this result, and you can obtain this result simply differentiating this equation to m times, assuming that m is a positive integer, and then we will get this equation 3. Now you can write this lambda equal to n into n plus 1 as you have seen earlier. So if we will write lambda equal to n into n plus 1 in this equation, then our result will be what? You can see easily. So writing lambda equal to n times n plus 1, the above equation equation 3 will become what this will become. You can see we will simply substitute at the place of this lambda n into n plus 1, and everything will be at each apart from this. So you can write this equation directly now. This is 1 minus x square into d2 dx square dm dxm Pn of x minus 2 times m plus 1 x d dx and dm dxm Pn of x plus, at the place of lambda, now we will write what? We will write n into n plus 1 and minus m into m plus 1 Pn of x, and that equal to 0. And so let us say this is equation number 4. Now you can see this equation is just identical to the Legendre equation. So when we will in fact compare, not Legendre equation but associated Legendre equation, you can say. So when we will compare this equation 4 and the equation which is defined here in equation, in fact A, you can see here A, and in fact this equation A is associated Legendre equation. So when we will compare these two equations, then what will be our result? You can see. In fact, not A, but we should compare it with equation 1, not with A. See here. This is our equation 1. This is in fact in this form, because here is minus 2m into m plus 1. So we should compare this equation 1 and this equation number 4. So after comparing the equation 1 and 4, you can see that at the place of f of x, there is in fact dm dxm pn of x. You can easily see. So comparing equation 1 and 4, we see that what you are seeing after this comparison, you can easily see that this is f of x is equal to dm dxm pn of x, and say this is equation 5. So you have recognized this arbitrary function f of x. You can see this f of x is what? This is the mth order derivative of Legendre polynomial Pn of x. So when we will differentiate this Pn of x m times with respect to x, then we will actually get this function f of x. And you can see we have assumed that m is positive. Now it is possible that m may have negative value, but we can write the result for f of x when m will be negative directly just observing this equation 5. So now let us consider that our m is now negative. So how we can decide what will be the expression for this f of x when m will be negative? For this, you can see the associated Legendre equation which we have defined here in equation A. In fact, you can see this equation A contains the term m square. You can see here, there is m square here, and so as m square is contained in this equation, and this m square will have positive value when m is either negative or positive, because you know a square of any negative is also positive. So since this equation A contains m square which has the same value for minus m and plus m, so the value of this that f of x, capital F of x, for negative value of m will be same as that for the corresponding positive value of m, because the equation contains m square, and m square will have same value when m is either positive or m is either negative. So you can say when m is negative, then what will be our result for this f of x? So you can decide it. As I have told you that as equation A, that is associated Legendre equation, contains m square, and this m square has the same value for plus minus m. So the value of f of x, that is capital F of x, for negative value of m will be same as that of for for the corresponding positive value of m. For the corresponding positive value of m. So you can write this f of x in case of negative m, that this f of x is equal to d mod m dx mod m Pn of x. Just like this equation which I have defined in equation number 5, you can write the expression for this f of x when m is negative. And so I hope you have understand why I have written this mod, because in this case the value of fx will be same when m is either positive or it is either negative, because the equation, the associated Legendre equation actually contains m square, which has the same value for plus minus m. So let us say this is equation 6. In fact, as I have told you that this capital Fx, which has been defined in equation 5 and in equation 6 for positive m and negative m. So to allow for the negative m, we can write the equation which have been defined in equation b. You can see here in this particular manner by using the sign of mod. See here this equation b. This is in fact f of x equal to Pnm of x, and that equal to this much. So if you will allow both the positive and negative value of m, then we will simply replace this m by mod of m. Then actually this equation b will be valid for both of the values, that is positive value of m and negative value of m. So you can say to allow for negative m, we can write equation b as, how we can write? We can write that this Pnm of x is equal to what? 1 minus x square to the power mod of m over 2 into f of x. And as we have defined this f of x in equation 6, so you can use this expression of f of x which is defined in equation 6 here, and in that way you can define the associated Legendre polynomial Pnm of x. So using equation 6 in this equation 7, using 6 in 7, what we will get? Pnm of x is equal to 1 minus x square raised to the power mod of m by 2 f of x. But f of x, you can see this equation 6. This is d mod m dx mod m Pn of x. So this is the defining equation of associated Legendre polynomial, and you must remember this result. You should remember this. This is a very important result because it is the defining equation of associated Legendre polynomial. So you can see, if you know the value of the Legendre polynomial Pn of x, then using this formula you can find the corresponding value of the associated Legendre polynomial. So in this equation, this Pn of x you know is known as associated Legendre polynomial, and these Pn of x, as you have seen, these are actually the solution of associated Legendre equation. So this is the defining equation. You know this Pnm of x are what? These are associated Legendre polynomials. And as I have told you, you must remember it, because in physical problem you directly write this expression for Pn of x. So to find the value of Pnm of x, you should remember this formula. Now you can see a particular situation here. In fact, there are two integers n and m, and we have to differentiate this Pn of x, in fact, m times, you can see here. So if you consider that the mod of m is greater than n, if we consider if mod of m is greater than n, then what will be the value of d mod of m dx mod of m Pn of x? Actually, this will be simply equal to 0. Why? You can see it. If this condition will hold, that is mod of m is greater than n, then when you will differentiate this Legendre polynomial, in fact m times or mod m times you can say, then definitely the result will be 0. Because you know this Pn of x, that is Legendre polynomials, Pn of x are actually polynomials of degree n. And so if we will differentiate it n times, then we will get a constant. Since Pn of x is a polynomial of degree n. So when you will operate the operator dn dxn on this Pn of x, the result will be a constant. And if you will differentiate it m times and you have assumed that m is greater than n, then it means you are differentiating a constant. And when you will differentiate a constant, the result will be 0. So you can say this dm dxm Pn of x, this will be equal to 0 if mod of m is greater than n, because in that condition you will have to differentiate a constant, and derivative of constant is 0, you know. In fact, to clarify this idea, I am giving some proper example. Let us say that we are considering a Legendre polynomial of degree 2. You know, you have already studied the Legendre polynomials, and you must remember the value of the second degree Legendre polynomial. You know, P2 of x is equal to what? You can say this is 1 over 2 3x square minus 1. 3x square minus 1. So you can see here, in fact, n is equal to 2. Now consider that m is mod of m. It is greater than 2. Let us consider. For example, you can take that m is equal to plus minus 3, m is equal to plus minus 4, and so on. You can take. So you can see when we will actually differentiate this p2 of x 2 times, then you will see 2 times means n equal to 2, then you will see that result will be a constant. You can see it. Let us find dp2 of x dx. What will be this? You can see actually this will be 1 over 2, and we will now differentiate it. So this will be 6x, because dc of 1 will be 0. So this is simply 3x. And if now you will find d2p2 by dx square, then what will be that? That will be d3 dx by dx, and that is 1, so this will be 3, and you can see this 3 is a constant. So what you have seen here, if the Legendre polynomial is of degree 2 and we differentiate it 2 times, then our result is constant. Now if we will differentiate it 3 times, it means we will differentiate this constant 3, and when you will differentiate this constant 3, you will get 0. If you will differentiate it 4 times, then again result will be 0, and that is why it has been said here that when mod of m is greater than n, then when you will differentiate this Legendre polynomial Pn of x m times, certainly your result will be 0. So I hope you this fact has been clear to you. You can see here. Now I am going to find the value of d3 p2 by dx cube. It means m is 3. You can see this will be simply d dx, and what is the result here? This will be 3, and that will be simply equal to 0. So now I hope you have understand this idea that this derivative of Pn of x m times will be equal to 0 when mod of m is greater than n. So in this condition, there is a restriction on the value of this m, because when this factor will be 0, you can see the definition of the associated Legendre polynomial. In fact, if this factor will be 0, then this associated Legendre polynomial will become 0. So now finally you can write here that Pnm of x, this will be equal to 0. This will be equal to 0. But when? You can write if mod of m is greater than n, then your associated Legendre polynomial will definitely vanish. That will be 0. And this is the cause that there is a restriction on the value of m. M has particular allowed values, and that allowed values of m depend on the value of n. So you can say that for non-zero finite solution of associated Legendre equation, or you can say that for the non-zero finite value of associated Legendre polynomial, what should be the value of m? What will be the range of value of m? Now you can decide it. So thus for non-zero finite solutions of associated Legendre equation, or in other words you can say for non-zero values of associated Legendre polynomials. Associated Legendre polynomials. What should be the value of m? Definitely that should lie between minus n and plus n. Minus n should be less or equal to m, and that should be less or equal to n. Because you have seen when modulus of m is greater than n, then actually this associated Legendre polynomial becomes 0. They vanish. So this is the restriction on the value of m, or you can say the allowed values of m. Now after getting the result for the associated Legendre polynomial, now we will see here some of the proper associated Legendre polynomial, or you can say expression for some of the associated Legendre polynomials. So now you can see expressions of some associated Legendre polynomials. Because we need at different places such type of value directly. So I am discussing here the expression for some of the associated Legendre polynomials. So see here. First of all, we will see the expression for Pn0 of x. Pn0 of x. It means here in this expression, m is equal to 0. M equal to 0. So now, using the definition of associated Legendre polynomial, you can find the expression or the value for this Pn0 of x. So you can see here. What is actually the definition? You can see. We know, you have just seen the definition. Pnm of x is equal to what? You have seen. This is 1 minus x square. 1 minus x square to the power mod of m over 2 into d mod of m dx mod of m Pn of x. Now, in the present example, we have considered we have to find the expression for Pn0 of x. So, here m will be equal to 0. So, you can write from here if Pn0 of x equal to what? We will simply substitute 0 at the place of m everywhere. So, you can write this is 1 minus x square 0 over 2 d0 dx0 Pn of x. Now see, when you will raise the 0 power on 1 minus x square, you know this will be simply 1. And what this operator means, d0 dx0, it means we have to differentiate this Pn of x 0 times. And when you say we will differentiate Pn of x 0 times, it means you will not differentiate Pn of x. So this operator means no differentiation. And if no differentiation, our function Pn of x will remain same. And so you can see that Pn0 of x is simply equal to Pn of x. This is a very remarkable result, and you can take several examples here. Let us say we want to find the value of P00 of x, P00 of x. So if we consider n also 0, so this will be P0 of x, and you know what is P0 of x? That is simply equal to 1. You have already studied this Legendre polynomial. If you consider that this is P10 of x, what will be this? You can see here, this will be simply P1 of x. And you know the first degree Legendre polynomial is simply equal to x. You have already studied it, so remember. And if you write P20 of x, what will be the result? You can see this will be simply P2 of x, and you know this P2 of x is simply equal to 1 over 2 3x square minus 1. So in this condition, when m is 0, then associated Legendre polynomial is simply equal to Legendre polynomial. So you can see this. Now I am writing some of the expression for Legendre polynomial mode. So let us see. If you want to find the expression for P1 plus minus 1 x, as you have seen that for both the positive and negative value of m for same value, actually the Legendre associated Legendre polynomials are same, and so I have taken at the place of m plus 1 and minus 1, because in both cases the associated Legendre polynomial will be same. So here in this example you can see your m is equal to plus minus 1. So now let us use the formula. You know associated Legendre polynomials are defined as 1 minus x square to the power mod of m by 2. Here m is in fact plus minus 1. So if you will take a mod of plus minus 1, that will be simply equal to 1. But I am writing it plus minus 1 divided by 2. And d mod of m is plus minus 1. So take the mod of plus minus 1. dx plus mod of plus minus 1, and Pn of x, you can see here n is equal to 1, so this is simply P1 of x. So what will be your result? You can see here, this is 1 minus x square to the power. Modulus of plus minus 1 will be simply 1, so this is 1 by 2. And again here, this will be simply mod of plus minus 1 is 1. So this is d dx P1 of x. But you know P1 of x is what? This is actually equal to x. And so dx will be 1. And our result is 1 minus x square to the power half. So P1 plus minus 1 x is simply equal to 1 minus x square to the power half. So this will be our result. Similarly, you can evaluate other expressions for the different degrees associated Legendre polynomial. Now finally, I am mentioning here some of the important properties, and you should definitely remember these properties, because whenever you will find its application at different places in physical problem, then you will write those properties directly. So you must remember it. So I am without proof, I am mentioning some of its important properties. So see it. Important properties. Not I am mentioning here all the properties. In fact, I am mentioning only those properties which are actually of our particular interest. So see, the first property I am mentioning here is Pn minus m of x is equal to minus 1 to the power m n minus m factorial over n plus m factorial Pnm of x. Remember it. The next property is Pnm of minus x is equal to minus 1 to the power n plus m Pnm of x. This is also a very important property. You must remember it. The third property I am mentioning here, Pn0 of x is equal to Pn of x. Actually, this property you have already seen here. You can see that Pn0 of x is equal to simply Pn of x. But I am in this list of important property, I have again written it. But you have understand this property very well. Now, the fourth important property of associated Legendre polynomial I am mentioning here. This is Pnm plus minus 1. Plus minus 1. Because you know x has the limiting value plus minus 1. You have seen earlier that this minus 1 is less or equal to x, this is less or equal to 1, because in this range of x only there are actually the finite solution of associated Legendre equation. So when we take this x equal to plus minus 1, in fact then this will be equal to 0 for m greater than 0. This is a very important property. Now I am mentioning the most important property of associated Legendre polynomial. Actually, this is known as orthogonality property. Orthogonality of Pnm of x. You have seen the orthogonality property of Legendre polynomial. Now we are giving here the orthogonality of associated Legendre polynomial Pn of x. In fact, it is defined in this manner: integral from minus 1 to plus 1 Pnm of x times Pn prime m prime of x dx, and this is equal to 2 over 2n plus 1 times n minus m factorial over n plus m factorial into delta nn prime into delta mm prime. Remember it. In fact, you know this delta nn prime and delta mm prime are what? You know it. In fact, these are Kronecker deltas. Kronecker delta. And you know what are its values. You know that this delta nn prime will be equal to 0 when n is not equal to n prime, and this is equal to 1 if n is equal to n prime. You know it. And similarly, this delta mm prime, this is also equal to 0, but when m is not equal to m prime, and this will be equal to 1 when m is equal to m prime. So these are some of the important properties of associated Legendre polynomial. and I hope you have got the idea of associated Legendre polynomial. So remember these facts and use these facts in physical problem, and after that you will be well acquainted of these facts.